Hi guys, today we're going to be discussing stereoisomers. These can be classified into two main types, geometrical or cis-trans isomers and optical isomers. In this video, we're specifically going to be taking a look at geometrical or cis-trans isomers. Now the condition for a molecule to be a cis-trans isomer is that the double bonded carbons need to have different groups attached to them. So over here, if you take a look at the carbon I'm highlighting in white, it has two groups attached to it. There's A and then there's B. Now if this group over here was an A, it would not be classified as a cis-trans isomer because the groups would not be different. So the groups that are attached to this carbon over here need to be different from each other. Similarly, if you look at this blue carbon over here, it has two groups attached to it, A and B. And both of these groups are different from each other. This group cannot be a B group because the groups are going to be similar and then it's not going to be classified as a cis-trans isomer. So just to recap, the double bonded carbons need to have different groups bonded to each other. That means these two groups need to be different from each other. You can have same groups bonded to different carbons but not to the same carbon. The next point is that the pi bond restricts rotation. So if you have a carbon-carbon double bond over here, and because of that, you're going to have hindered rotation. A cis isomer is when similar groups are bonded on the same side of the carbon-carbon double bond. So if, in this case, this is going to be classified as a cis isomer because you have same groups on the same side of the double bond. And a trans isomer has similar groups diagonal to each other. And we're going to be discussing more examples of cis and trans later, so it's fine if you don't understand it just now. Now we're going to be taking a look at some examples of cis-trans isomers. So this is the first one we're going to be taking a look at. If you divide this into two parts, one of them referring to the groups attached above the carbons, and one of them referring to the groups that are attached below the double bonded carbons. Now previously we talked about how if same groups are attached on the same side of the carbon, in this case it refers to above the carbon, it's going to be classified as a cis isomer. So now let's name this. This has 4 carbons and the double bond is on the second carbon. So this is going to be classified as cis but 2-ene. Now let's look at the next example. If you do the same thing for this and you divide this into two parts, one of them referring to the groups above and the other one referring to the groups below, you can see that similar groups are attached on different side of the carbons. One hydrogen is above and one hydrogen is below. Similarly, one methyl group is above and the other one is below. So this is going to be the same thing. It's just this molecule in a trans notation. So if you name this, what are you going to get? It's going to be trans but 2-ene. So both of these are going to have the same molecular formula. It's going to be C4H8. However, the name is going to be different because one of them is cis and the other one is trans. So both of these are geometrical isomers of each other. Let's take a look at another one. Now if you look at this one, same groups are attached to one carbon. Because of that, this is not going to be cis-trans. It's going to be just a structural isomer. So all three of these, if you take a look at it, even this has 4 carbons. So the formula for this will also be C4H8. So all three of these are going to be isomers of each other. These two are going to be cis-trans and this one is going to be a structural isomer. Now let's take a look at this. In this case, if you do the same thing, if you divide this into two parts, one of them referring to the groups attached above and the other one referring to the groups attached below, you're going to see that same groups are attached on the different side of the carbons. So because of that, this is going to be classified as a trans isomer. Now moving on to the next example, if you divide this into two parts, above and below, you're going to see that the same groups are attached to on the same side of the carbon. So because of that, it's going to be cis. Now, even though the molecular formulas for these two are going to be the same, they're both going to be different because one of them is trans and the other one is going to be cis. So both of these are cis-trans isomers of each other. If we take a look at this, you have same groups attached to the same carbon. So because of that, this is also not going to be cis-trans. So the next important thing that you need to note is that cis-trans isomers have the same chemical properties but different physical properties. So properties like boiling point, density, melting point will all be different. The next thing that we're going to be talking about is the rules for assigning priority when all the groups attached to the carbon are different. So previously we looked at examples like this. In this case, the groups that are attached to the carbons are the same. You have hydrogens and you have methyl groups. However, if you have an example like this, in which all the groups are different, there's a methyl group, there's an ethyl group, there's a bromo group, and there's a hydrogen group. So because of that, the rules are going to be different. So the priority is going to depend on the AR of the atom directly attached to the double bond. So now let's mark the atoms that are attached directly to the double bond. In this case, there's this carbon, there's a bromine, there's a carbon, and there's a hydrogen. And now let's write down the AR of each of these to determine the priority. So in this case, the AR of carbon is going to be 6. The AR of bromine is going to be 35. Again, the AR of carbon is going to be 6, and the AR of hydrogen is going to be 1. So as you can see over here, this bromo group is going to have the highest priority on this side, and the carbon is going to have the highest priority on this side. So now if two high priority groups are going to be on the diagonal side, it's going to be trans, right? So in this case, this isomer is going to be classified as a trans isomer. Now there's another rule which does not apply to this particular compound, but the next compound that I'm going to be discussing. Now if two atoms are going to have the same priority, so for example, if this carbon and this hydrogen, if instead of this hydrogen you had another carbon over here, then these two carbons would have the same priority. So you would look at the atoms that are next in line. And we're going to be talking about an example like this in the next slide. So now we're going to be taking a look at a few more examples. This is the first one that we're going to be taking a look at. So now we're going to be marking the groups that are attached directly to the carbons. So there's a hydrogen in this case and a carbon in this case. Now the carbon is going to have a higher priority because it has a higher AR. Next, we're going to be moving on to the other carbon. So now both of these carbons have the same group attached to them, which is carbon. So what we're going to do is we're going to move to the next group. So the next group that's attached there is a hydrogen, and in this carbon it's also a hydrogen. Since both of these are the same, we're going to move away. So the next group that you have over here is a carbon, and over here there's a carbon. Now there's no other group attached after it, whereas there's a chlorine attached over here. So that means that this group has a higher priority. So this is going to be a cis isomer. Now let's take a look at the next one. So if you highlight these carbons and you look at the groups that are attached to them, you're going to see that in this case, you have two carbons attached. So you're going to move away. Over here you have hydrogens. This is the same group. This is the same group. This is the same group. And this is also the same group. However, on this side, you have one extra methyl group attached, and over here there's nothing. So this means that this side has a higher priority. Now let's take a look at the next carbon. So these carbons are bonded directly. So if you move away, you're going to see that you have hydrogen bonded on this side and you have 2 carbons bonded over here. So this means that the group above is going to have a higher priority. So this is going to be a trans isomer. So just to recap, you look at the carbons, you look at the groups that are attached directly, and if those groups are the same, like in this case, you move away from the double bond and you compare the succeeding groups, and you compare those and you assign priority based on that. And then you see over here, since 2 high priority groups are attached on the opposite sides, this is going to be trans, and if they're on the same side, then it's going to be cis. So these are the rules that you follow. Now let's take a look at a few important rules. So if they give you a skeletal formula in your examinations instead of drawing it all out for you, and it looks like this, which slightly resembles a chair, this is going to be cis. And if it looks like this, which slightly resembles a boat, this is going to be trans. Now let's take a look at a few examples. So all of these 4 compounds that I've drawn, they're all isomers of each other. They all have 9 carbons. So all of these are non-dienes. However, they're all going to be cis-trans isomers of each other. So let's take a look at the naming of these. So as you can see, this part over here looks a lot like a boat. So this is going to be trans. And this part resembles a chair. So this is going to be cis. So the notation that you have in this case is going to be trans, cis. Let's take a look at the next one. So for this one, this slightly resembles a chair, which is inverted. So even if it's inverted or flipped, it's still going to be classified as cis, so you don't need to worry about the shape of it. And this looks very similar to this, so this is going to be trans. So in this case, this is the trans-cis notation and this is the cis-trans notation. So even though the molecular formula for all of these is going to be the same, they're all going to be isomers of each other because one of them is trans-cis and the other is cis-trans. And we're going to be taking a look at more of these. So this is trans and this is also going to be trans because it resembles this shape over here. So you're going to have trans-trans. And if you take a look at the last one, there's a cis over here and the same shape over here. So this is going to be cis, cis. So in this case, you have 4 isomers. So you get the formula 2 to the power n, where n basically represents the number of carbon-carbon double bonds that can exhibit cis-trans isomers, cis-trans isomerism. Now this means that they need to have different group attached to each of them. So if you take a look at this example, there's 2 carbon-carbon double bonds. So 2 to the power 2 is 4 and you have 4 groups. So in questions, like usually in MCQs, when they give you these double bonds, you don't need to sit down and draw all of these structures. You can use this formula. But one thing that you need to be very careful of is that the double bonds need to be able to exhibit cis-trans isomerism, which means that different groups have to be attached to all of them.